the particular thing about the quantum bicycle project was to have a look at the relationship between what electrons made of, what's light made of, how does it work. And where we started was with Martin and myself back in the 90s, is we started with the idea, with the conjecture, and that's what you do with a theory, you just make some stuff up. And then you see how far that gets you, that particular conjecture, and how closely it corresponds with experiment, with what you actually observe. And what we conjectured is, we conjectured that matter was made from light. Now this turns out, in my 2018 view, not to be the whole story, but it is a good part of it. That it's not just made from light, but there's more to it than that. So what we thought back then, and what we conjectured back then, is we thought we knew quite a lot about light, because Martin's an expert in light, and I thought I knew quite a lot about particles, because I was an expert in particles. So what we did is we had a look at the structure of light. And let me just see if we get something here which is perhaps more sensible. This is a picture of the creation event of two electron-positron pair of matter from light, or alternatively, of the destruction event where matter goes into light. So light to matter, or matter to light. So you can read it either in come two photons, these are the photons, the straight lines, and that produces an electron-positron pair. These are these rings just here. Or that the two rings unravel and give you light. You can run it forwards or backwards in time. And both processes happen. So what we did in the first instance is and I'll go back a few slides to this one, because this is going to be a picture of what I'm just going to make here. What we did is we looked at light, and we knew that light contained electric and magnetic fields. It's electromagnetic. And we also know that a circularly polarized photon, that's a photon that has a spin of 1 unit of angular momentum, h bar, has a structure whereby you have an electric field perpendicular to a magnetic field, and that electric and magnetic field spiral through space, each one sweeping up the other one behind it and creating the other one in front of it. So electric changes to magnetic, magnetic changes to electric in a balance, and this balance is described by an equation, and the equation expresses that balance in mathematical terms, whereby the electric field can change, fine, provided it gives you magnetic. And the magnetic field can change, provided it gives you electric. And then having both of those, you have a wave. Waves from one end to the other, from one thing to another thing. And that wave screws through space, spirals through space, producing this wonderful spiraling of electromagnetic field, of the shape of, let's go back to this thing just here. Oops, I didn't know I got that. So you have a spiral coming in, and I'll just make a model of it. So here's a piece of plastic. So we can make a twist in that piece of plastic, which looks like part of a spiral. So, and what the photon looks like from the outside is, it looks like, imagine an electric field poking up on the top of this strip. So if I twist it, then the electric field does a spiral. And you can imagine the magnetic field sticking out sideways just here. And that does a spiral too, but a spiral 90 degrees apart from the electric spiral. So that's what the photon looks like, and that's what the thing, you can measure this. So measure what the electric field distribution looks like in space by sticking a thing in a cavity and just measuring electric field. So that's what they look like, and we've known that for a long time, since Maxwell, which is 1870s. So, so this thing comes in, and what we thought happened, and we still think happens really largely, is the two photons come in, one screwing one way, the other screwing in the same sense but in opposite directions, so they're actually moving in opposite directions with respect to one another. And what they do is they hit each other and they mix. And instead of having an electromagnetic wave going left to right and one going right to left, you now have two oscillations which mix with one another. So one of them goes, so one of them's going leftwards, the other's going rightwards. And what you get is, instead of going left, 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 and right, 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 you get them splitting up into two bits, one which goes right, left, and the other one goes left, right, backwards and forwards, thus confining them and actually changing the shape from being a spiral through space like this to being something which comes back and bites its own tail like this. This motion, so I've taken a twist, a single twist, and I've just turned it around so that something is making it go round, and what you get is, naturally, is you get this double loop. Now the twist is still in there. If I look at a bit of the double loop, I can still see the twist. But what the twist has done for me is it's made it go zip, zip round twice. If I don't put the twist in and do the same thing, I just get a single loop. But putting the twist in, a whole twist in, and putting it in, I get this double loop. Now this double looping motion of the electromagnetic wave twisting, but as it twists, it also turns. It also turns like this. That twist plus that turn does something spectacular to the electric field of the photon. It means the electric field now, look at it, it's always directed out from the inside. It's outward directed in this case, if we take it sticking up from this strip. So it goes to something which has an electric field sticking out like the spines of a hedgehog, going out in all directions. That's the characteristic of what a charge looks like. A charge has the electric field either sticking out if it's positive, or sticking in if it's negative. That object is charged, and you can calculate that charge. It also spins, spinning round and round, zzz, 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 and it's charged. It's got the electric field sticking out. So what we did back in '97 is we calculated the spin and we calculated the charge. We found the charge was very close to the electron charge, and we found the spin was exactly the spin of the electron. So we identified that thing, and that is this object just here. This double looped thing is this thing just here. Then putting in the fields, pricking outwards, sticking outwards, then you see this is this object just here. You have the same double loop. The green spines are the direction of the electric field, and they're sticking outwards for one of these two things, and they're sticking inwards for the other one. This thing's charge negative, that's charge positive. Net charge going in is 2 uncharged photons. Net charge coming out is +1 -1 is also 0, but in a different configuration, a configuration where the field has become outward facing and hence produced two charged objects, an electron and a positron. So this was Martin and my model back in the 90s of what matter was, what an electron was. And this is the idea, the picture of how electron positrons create one another. And the paradigm, the model really is, the analogic model of this is that you have a flow of stuff which goes around a double loop like this. And in fact it's more than that, it goes around a torus, it goes around a donut. So we're going to come into this later, I'll show you where the donut is. But you can actually run a donut through this, and it goes over the surface of a donut-shaped thing. And there are a whole set of nested donuts as well. So this is a toroidal loop, or a loop on a toroidal surface, on a donut-shaped surface. That's very important, and we'll come back to that later. But that's the basic idea of what the quantum bicycle is. In a typical atom, well, a hydrogen atom is one proton with one electron. Now, the school view, the simplest view, the old-fashioned view, the Bohr model of the hydrogen atom is that you have a proton with an electron going around it like a planet goes around the sun. So that's, but it turns out that if you take that more deeply, it turns out that the electron doesn't go around the proton. What it is, it's like a proton has an electron cloud quantum mechanically surrounding it. So you can imagine it will be as though the Earth was not like a little hard thing going round and round the sun, but that the sun blew up and the Earth blew up, so the two things were actually merging through one another. That's what it looks like quantum mechanically. So, but these are different models of what's happening. So the atom is an atom. It doesn't matter what you think about it, it stays the same. These are different ways of looking at. See, humans, you can't directly see an atom. Because, why not? Because light is 10 to the minus 6 meters and atoms are 10 to the minus 10 meters. So it's like trying to see mice by dropping elephants on them. So you know, you just, photons are great big things and atoms are really little things. You know, what? Nothing. Didn't notice the mouse at all. So so you can't directly see it. You can't see it with light. It's too small.
How do we see it then?
Use electrons. But you see the electron is what it's made of as well. So what you do is you fire the smallest thing you've got at it and see what that does. But that's like trying to find out where people are by firing people at them. Right? I'm using analogies. But you know, okay, so where was the person? Well, okay, it depends on whether the person hit was a rugby player or not, right? So you don't know by... so the lightest thing you can use is an electron, but that's already part of the... And that's the problem. The problem is that you can't see it directly. You have to imagine it, and then work out what that would be if that were true, and then see if, as I say, your idea of reality corresponds with what you actually see, with what you actually measure, what you actually can measure. And a lot of the uncertainty principle in quantum mechanics, I think you'll have heard about uncertainty and how everything's random at some level, and Schrodinger's cat, alive or dead, and stuff like this, popular science. That comes from the fact that the stuff that you can't know because you can't measure it. So something is happening, but you don't know what, because you can't say, okay, it's exactly at this point in the cycle. It's like knowing the engine's going round and round, but not knowing exactly where the piston is right now. And why would you want to know anyway? You don't want to know exactly where the piston is at the moment. You just want the car to go around the corner, right? Or speed up, or get out of the road, or something. So it's like that. So, okay, that's the basic idea. Oh, wait a minute. I really should take this out, actually, because this is kind of... Okay. Right. I think... This is where you want to be, the current understanding of what they are.
That may make it easier for me.
Okay, I'll tell you what the current understanding, or the current pictures that we have of electron. So what I had here in the introduction was really the rest of the quantum bicycle project. I'll go through it very quickly and say what I was going to say. Mm-hmm. That's the picture. This is taking these double loops and having a look at what an electron looks like in this model. So this is looking in more detail at this shape. And I've put some smoke rings in here just to show how this motion goes round a toroidal shape. This is like a donut, like a sausage. And it's on the surface of that series of smoke disks. So the series of smoke disks, if you imagine them coming through here, form a toroidal shape if I extended the smoke disks. And then the stuff gets projected down to a spherical thing in the reality in which we observe things. So this is, I mean, it's a donut. It's like you know what a donut looks like? It's a curved surface, but it's a curved surface with a hole in it. Mm-hmm. So it's a torus is donut shaped. So donut's got it's a ring with a hole. Let's make one. Yeah, bagel's just what you need. It's okay, I've got plasticine here. Make anything. So I'll make a slightly smaller one, I think. Okay, so you have something which is ring shaped, like that. And what happens is this motion takes place over the surface of a ring. It comes in and out over the surface of a ring. Want to see what it looks like?
Yeah.
Four-dimensional rotation. Just a minute. Let me just come out of this and go over here. Here we are. So what this is you know, okay, this is going to blow your mind slightly, but that's okay. Don't worry about it. Right. So imagine a bicycle wheel, and the bicycle wheel's going round and round. Okay. So it's rotating like this, and that's a two-dimensional rotation. It's a rotation in a plane. Now, in 3 dimensions, you can't have 2 rotations happening. If I try and rotate that thing so it's rotating about the axle. But imagine I try to put another axle into the thing and have it rotate about that as well. Right, stick a spoke through the wheels. Mm-hmm. Doesn't work. Bicycle wheel stops rotating. You can't have 2 axes of rotation about which it's rotating at the same time. You could spin the whole bicycle and things, but that's not what I'm talking about. I'm talking about having a separate rotation in a completely separate plane. Why?
Like a gearbox?
Well, no, not like a gearbox, because I'm talking about having a rotation. If I'm rotating like this in a plane, that plane's got 2 dimensions in it, and the rotation's happening in the two dimensions. If I want to have an independent rotation, I've only got one more dimension. So because I've only got 3D. So you can't have 2 rotations going on at once in 3D, because you've only got one. Because if the rotation is happening in a plane, there isn't a separate plane not connected to this plane. You've always got to have part of that plane too. But in 4 dimensions, and space as time is 4-dimensional, you have got a separate plane. If this is the XY plane, I've still got the ZT plane I can rotate in. So what that is that's a motion. Now, that's hard for us humans to do, but it's easy for a computer. So just, so you just say, okay, there are 4 dimensions. It goes, yeah, sure, 4-dimensional vector, no problem, just an extra component. So what you then do is you do 2 rotations and you project them. Okay, and this is what happens. This is what, look at this thing here. Look, I can make this thing longer or short. This was actually done by a guy called Fergus Murray. I downloaded it, it's open source, so I've modified it to be able to do this kind of thing. So I don't know if you can see that little thing wobbling around just there. You see what it's doing? It sort of, looks, this is a projection of a 4D rotation. But let's make it longer so we see what it starts.
Blowing in the wind.
It does, doesn't it? But look, if I make it longer, look, there it is. Do you recognize that shape? It's that thing. Okay, now I'm going to make it longer. I'm going to let it keep on doing this. All right, so I'm just making it longer than one thing. So I'm following the path, just making the path go for longer. You're looking at a 4-dimensional rotation, but then projected onto the screen and project into time. Look what it's doing. Can you see it kind of like it's folding around something? What it's folding around is something like that, a torus. So the rotation is going around this, but then as it moves around, you're looking at different projections of this. And if you imagine something, imagine a ball, a sphere of metal, 3-dimensional sphere. Imagine a circle. I can make that 2-dimensional, squash it down, it's just a circle of metal. Turn it into a sphere, it's a 3-dimensional thing. I can do that again, I can make it mathematically, on the computer, make it 4-dimensional. And then if I look at and that's what I'm doing here, I'm looking at the projections of something going around that 4-dimensional sphere. So, and those projections have 2 forms. One of them is, well, just like if I take a sphere and I project it straight down onto a surface just here, I'll get a circle. But if I take your light and I project it that way, I'll get an ellipse, or a different kind of shape. So circles don't just produce circular projections onto a plane, they can produce things that are elongated as well. Try it. When you do that with 4D, you can get circular, spherical. So a 4D sphere goes down to a 3D sphere in one projection, but on any other projection it goes to a torus. So projections there become toroidal, they have a hole in them. So the projections of a 4 sphere are either toroidal or spherical. And that's what you can see here on this flat thing here, that it's really just, it's going around a torus. And you can show that mathematically as well and prove that it's a surface, but that's a bunch of heavy maths, so why would you want to look at that? This is much more fun. And actually the maths isn't very complicated, it's just a few sine waves, sines and because all a circular motion is it's x is a cosine wave and y is a sine wave. So if you do x is cos theta and y is sine theta, it just describes a circle mathematically. So these are just sines and cosines, and all you do is, instead of having 2 of them, you've got 4. So it's not particularly hard maths. But we're stupid humans, so it's very hard for us to see 4D, but it's not hard for the computer to generate it and then project it.
Because I've never seen.
We've never been outside 3D, have we? No, and we never will, because the world is 3-dimensional. It's not 4-dimensional, despite, which we'll come to later. A language allows you to describe things you otherwise couldn't describe. So, and that otherwise couldn't be understood. And where we are at the moment is kind of like this. If I switch language, als ik een andere taal ga spreken, dan begrijp je geen bal van wat ik zeg. So if I switch to Dutch, I guess you don't speak Dutch. So you don't get any of that. What we need to do is get to a situation where you need to develop the language which allows you to describe what's going on. And that's what I'm going to try and explain. Now, it's actually quite a simple, straightforward language, but it is... it's the language of mathematics, and that's going to be interesting. So what we're going to do is think of, okay, what I want you to do is think about an equation and what it means. So you have an equation like F equals ma or E equals mc squared. These are equations that have some sort of meaning. So let's take force is mass times acceleration. That's Newton's law. So what that equation tells me, it says if I apply a force to my car, of a certain amount, and that car has a particular mass, it'll accelerate at a particular rate. And the more force I apply, the faster it'll go. The less mass it has, the faster it'll accelerate. So force is mass, so it's force over mass is acceleration. So more force, more acceleration, less mass. Force over mass is the number that gives me the amount of acceleration that I get. So that's what an equation does, though, is it also expresses a balance. And to see that, if you write down, so if I write this down, so if I write down an equation, so we write down the equation F equals ma, force is mass times acceleration, that's one of Newton's laws. Then I can also write down, I can manipulate that equation and do F over m equals acceleration, dividing both sides by m. That tells me the rate of acceleration is given by the force divided by the mass. But I can do something else. I can take the ma to the other side. I can say F minus ma is equal to 0. And so force minus the mass times acceleration, what it's saying is that force is balanced by a counterforce, which is given by mass times acceleration. And we can show this, we could play, if we imagine we had a big ball here or something, the counterpart is also true. If I threw a ball to you, and you'd feel the force as it hits you, that's the mass, and acceleration is giving a force as it hits you. But what there is a balance between the force of you stopping the ball and the ball hitting you, which causes it to come to a stop. It's a balance equation. Equations are expressing some sort of balance. Now in light as well, remember what we were talking about before, we're saying electric gave magnetic, gave electric, gave magnetic. And there's an equation which describes that, which is also a balance equation, which says you can change the electric, but it's going to give you a changing magnetic because it has to be in balance. And that's expressed by an equation, which is Maxwell's equations, which expresses something very similar. Newton's laws here I can write in another way, which is force is equal to, and I'll write it like this is calculus. I don't know if you did any of this, but it's the rate of change of momentum. It's how fast momentum changes. So if you think about the momentum of a ball, if you can slow it down gently, you're changing its momentum slowly with little force. On the other hand, if you want to stop it fast, big momentum change, big force. So the rate of change of momentum is also the force. And once again, I'm going to put this to the other side. So I could do F minus dp by dt, by the change in momentum with respect to time, is equal to 0. And that's again force, and this is also a force. These are two different forces. And the equation is balancing everything in any equation is always the same stuff. So in this particular case, these are force equations. So force is a force, and then ma is a force, and dp by dt is a force. These are all different ways of expressing what's essentially the same force. So you write it in different ways, and write it as a balance equation, write it as an equation that gives you a value, or write it as a rate of change of something. Now what we're going to do is we're going to write down another equation that looks kind of like this, something equals nothing. So that something in this case is all force is balanced. What we talked about before is the whole energy of the universe remains in balance. It doesn't change. Energy is conserved. So the total energy of the universe remains the same as a principle. So the change in energy is equal to no change, is equal to 0. And that would be an equation. It's called a conservation equation, conservation of energy in this case. So that's what equations are doing. They're expressing something meaningful in a very, very short form, a very compact form. But you see, if you get an equation like this, look at this equation, it says dg equals 0. So what does that equation actually mean? Well, to know what it means, you need to know, it's got 5 questions that are immediately raised. You know, like what's g? Obviously. What's d? What's equals? What does equals mean in this case? What's saying something is nothing really mean? And also, what is 0 anyway? What's 0? So that equality has a meaning as well. And actually the equality doesn't mean is the same as. It doesn't mean that dg is the same as 0. It means that because dg can have all sorts of bits in it, it just means the bits of dg are going to have to be in balance. For any positive bit you get, you're going to have a negative bit that balances it to give you nothing overall. A plus bit and a minus bit. So that's what the equation is telling you. But also there's stuff in here as well. This is actually a differential equation, or going to be a differential equation. It's not the letter d times the letter g. That d is going to be a differential operator, a vector differential operator, which is like calculus, but then a vector calculus, which I know is complete Greek to you. But what it is, it's the d's are kind of division, d for division, and the g's are kind of reality, but the reality is going to be 16-dimensional. So it's actually going to look like a really complicated equation. And it is a really complicated equation. It's much more complicated than any of the ones we've gone before. But it's written in this very simple form in the maths. But what it means, forget about all the complexity, what it means is D means the change, the total change. And G means of everything. And equals here means has a value of, rather than is the same as. Nothing at all. So whatever changes, what it means is the change of stuff is balanced internally. Anything positive is negative. If I take you and push you, then I feel push on me. And that's a balance equation. If I push you, you push me back with the same force. It's a balance. So it takes me the same force to push you as I feel pushing you. So if we push, right, keep it still, we're both feeling the force. And that force is balanced because we weren't moving. So we have plus force this direction, minus force in that direction is zero force. We're not moving. So that's a balance equation. That's the kind of thing. But we could take that force and we could change it. We could say, how does the force change? I could push harder. So, and then that's the kind of thing, say it's talking about the change in stuff. And when we're talking about light, you're talking about how does light change? Well, what it does, it screws through space. And that's describing the change of the light. That's what the equation is trying to do. So what we need to know is we need to know what multiplication is here, because we've got something going into something is zero. Actually, that's the division of something into something is zero. What do these things, different things mean? Now, inside this differential, the differential is a vector differential. It's a differential which is going to be how does thing change in space? What's the spatial change of something? And also how does it change in time? Now, let me give you an example or an analogy, because which everybody's familiar with. We know what space is. You know how to measure space, measure it with a ruler. And we know what time is, something you measure with a clock. But what happens if you divide space by time? So we divide space, divide a ruler by a clock. Here's a ruler. Right. Take this ruler. Right. Going to divide it by this clock. Here we go. Space divided by time. What is that? What a ridiculous thing to do. What do we got? We've got half a meter by a second, meters per second, miles per hour. We've got something which is a velocity. Space divided by time is a velocity, is a speed as well if we don't specify the direction. So this thing has a meaning. Space divided by time has a meaning, and it's something which we're familiar with, velocity. But velocity is a very funny thing. It's not really a vector. It's something which has funny properties. You don't notice it usually, but if you're in a train going at 60 miles an hour and you're walking at 5 miles an hour in the direction of the train, to an outside guy, you look as though you're going 65. If you walk 5 miles an hour back down the train, you look as though you're going 55, 60 minus 5. So you can, at slow speeds, you can add velocities, but at very high speeds, you can't add velocities. It doesn't work. And in fact, you can't go faster than the speed of light. And this isn't like a sort of speed limit. It's like an absolute physical impossibility to go faster than light, because there's no such thing. And the reason there's no such thing as going faster than light is because space and time are not what you think they are. They're actually different parts of the same thing. And when you start doing that division and getting up to the speed of light, space and time change. They're not fluid, but they are flexible. They sort of bend. And they bend in such a way that the speed of light remains the same. And the reason they do that is part of the reason for this whole thing working. The reason is because the stuff that you're made of is the stuff of space and time in the theory. And because the things that are the things you use to measure stuff with are also the things that you're looking at, when you start getting up to the absolute units of those divisions, then the process no longer varies. It no longer changes, because what's happening is your measuring systems are changing in the same way as the thing you're trying to measure. So, so it's like it's like trying to get north of the North Pole.
It's like putting a plastic ruler in a boiling pot of boiling water.
Yeah. Why is that?
Because it's melting in the water.
Oh, it's melting in the water. You're right. It's like putting a sugar stick into water. Exactly. But it's like trying to go north of the North Pole. You can't go north of the North Pole because we're on a sphere and there is no north of North Pole. Everywhere is south from the North Pole. So it's kind of like that, as a not very good but nonetheless oft-used analogy. So the example here is, what does dividing space by time mean? You know, what do we mean by that? And we get something out of it, which is velocity, which has peculiar properties when you go nearly light speed. In fact, let me tell you what the peculiar properties are, because they're really, really spectacular. So this is an aside. The thing is, from Einstein's relativity, what happens is, as you go faster and faster, you get this thing called a Lorentz contraction appearing, which means that your measuring rods appear, they don't actually get shorter, but they appear to be shorter. If you measure them, they're shorter. Measure them from another frame, they're shorter. And what happens as you go faster and faster is a measure of length in space and time is given by, measured in meters. If you multiply time by the speed of light, meters per second times seconds, then you get something which is in meters. So measured in meters, the distance between two events, between two happenings, is given by ct squared minus x squared minus y squared minus z squared. It's given by time squared minus space squared. And at the speed of light, those two things are in balance, they're both equal. So that distance is 0 at the speed of light. Now what it means that if you're looking at the sun, you see the sun as it was 8 minutes ago, but you're seeing it with light which is coming from the sun. Now at light speed, any distance is no distance. Of course that thing gets shorter. So for that light, your eye was on the sun. And for you, the sun is in your eye, literally, right there, bang, touching. Because for that light, that space has been contracted by the Lorentz contraction down to nothing at all. And what that means, it means anything you see, if you're standing out on a starry night, is for you here and now. It's actually happening right this moment. That event of you seeing that star is that for that photon, the distance between the star and your eye was nothing at all, relativistically. So as you get up to that velocity, space and time do weird stuff. That's the bottom line of relativity. Anyway, what we're going to try and do is develop something like this equation, where I'm changing the mathematics so that it is as close as possible to what actually happens. About 500 years ago, in Western civilization, although there's quite a lot of evidence that the particular method was invented before that by the Arabs, there was some guys in the Italian Renaissance who couldn't read Latin or Greek, or couldn't read Greek anyway. And one of these guys was called Leonardo da Vinci. And he started using, either developed himself or thought for himself or found out from somewhere, a method of finding out about how stuff worked that didn't depend on reading about what the Romans or the Greeks thought about it. It didn't depend on learning it from some authority. And the method he invented, or he used in his researches, was what we now call the scientific method. And what that method is basically you make some shit up, you have a look at what happens. If they agree, your original stuff was a good approximation of what's going on. If not, you throw it away and you make some new stuff up that does agree. And you refine your model not by asking Archimedes or something, but by asking nature. What does nature say? And this process has proven so powerful that, despite the fact that Italian Renaissance technology at the time of Leonardo is roughly equivalent to Greek technology 2,000 years earlier, and the 2,000 years in between there'd been no progress, pretty much. People invented this scientific method, started using it. By the time Galileo, it was just common knowledge, everybody did it. And what that's produced is it's produced a bootstrapping of human understanding of how stuff works, which is exactly this process. What you do is you don't change reality. Of course, reality is reality. Obviously, you don't change reality. You change your view of reality. You change your way of explaining reality. And that continuous change is what we call science. Our understanding of how stuff works is just getting more and more potent at being able to build machines, steam engines, cars, then build computers, build lasers, build quantum devices, stuff that comes out of imagination, goes into the third world, becomes common knowledge, becomes something that you make in a factory. So, and that process goes on, but this is that method. You go back and you refine the way you think about things so you can think about it more effectively. So it's not cheating, it's the way. It's the scientific method. So this is where you came in. What's the current view of the electron and proton? What's stuff made of? Well, the kind of thing you learn at school is that, or the sort of way we look at this thing is that electrons and protons as little particles, tiny wee things. And the simplest view of the atomic world is that you have three kinds of particles: electrons, protons, and neutrons. These are little point things. Protons are pretty heavy. They're about nearly 2,000 times heavier than an electron. So are neutrons, a bit heavier still than the proton. Protons plus charge, neutrons zero charge, electrons minus charge. And the way atoms work is plus attracts minus. So you end up with a neutral. So atoms tend to want to be neutral. So hydrogen's one proton, one electron. Helium has got two protons, but it turns out that protons would just repel one another because they're both positive. You need something to stick them together. And the stablest form of helium's got two protons and two neutrons holding it together. So it's 4 times roughly as heavy as hydrogen. 2 protons, 2 neutrons, 2 electrons. Plus 2, minus 2, zero charge. Balance. Balance, balance, balance. Lithium's got 3 protons, 4 neutrons. 7 times the mass roughly of the hydrogen atom. Not quite, because there's binding energies involved. 3 electrons. And then you just go click, click, click. Lithium, beryllium, boron, carbon, nitrogen, oxygen, etc. Each has 1 more proton, and they're distinguished by having more and more of these particles. A little cluster. So the picture is a little cluster of electrons and protons with a cloud of electrons going around them. And depending on your model, you could say they're going around like planets. Little ball going, a little point going around. That's the simplest model. Next one up is, and it's quite a long way up. The next one up is quantum mechanics, where you say, okay, the electron's really a wave, so it sort of wavies around it. And it turns out that wave is actually a spherical wave, so it looks like a spherical bell. So it's sort of like the oscillation you get if you took a sphere and donged it. Does things like this, so it waves spherically. And those spherical waves are the solutions of the quantum mechanical electron around the proton. And actually the proton has a spherical bell shape as well. So the current picture is of these things is that they're sort of little particles, like little tiny dots. So that's the simplest picture. But it depends on which. So we have an idea of what these things look like. We can describe them mathematically in quantum mechanics as a wave. We can describe them. So we have a bunch of different theories which describe stuff. Quantum mechanics. So that's these things here. So in quantum mechanics, the electron's sort of a variable-sized wave. It can be a big wave or a small wave, but in an atom, it's roughly 10 to the minus 10 meters. It's 10 zeros and a 1 meters. In free space, it's roughly the Compton wavelength, 10 to the minus 13 meters. In the solid state, it can be a lot bigger. So it's quantum mechanically, it can be nanometers or even micrometers in size. So that's quantum mechanics. That the picture of the electron is it's sort of a wavy thing. Then, on the other hand, we have relativistic quantum mechanics. In relativistic quantum mechanics, here's the book by Dirac himself, who invented relativistic quantum mechanics. And what it looks like in relativistic quantum mechanics is one of them. A horrible equation. What the horrible equation means is it means that what the electron looks like is it looks like a little point thing that goes backwards and forwards very fast. Actually, it goes backwards and forwards at the speed of light. And this is first described by Schrödinger, I think. Anyway, it was described in German, so it's called a Zitterbewegung, which means in German, a zittering motion. So So that's what it looks like in relativistic quantum mechanics. In Maxwell electromagnetism, electrons really just act like a point charge, and they're the thing that emits light. In quantum electrodynamics, they are a point charge which also emits light, so similar to the kind of idea that we're talking about with just a little point electron. So in the standard model, there are lots of these little point particles, like protons composed of point quarks, electrons point particle, muons point particle, tauons a point particle. There are gluons, which are presumably also point particles, or act like point, well, except they don't, you can't scatter from them very easily. So there's a whole bunch of these things that are all thought to be sort of point particles in these more advanced models. But the problem is, you know quite a lot about it. We know what they look like, and we can do experiments on these things where you can measure the size and shape of these things. I did one myself in the 90s, where I looked at single electrons coming through in a solid state, and I could measure the charge profile of those electrons and see that they were distributed over tens of nanometers, individual single electrons, sizes of much bigger than atoms, many hundreds of atoms. One electron was distributed over hundreds of atoms in 3 dimensions. So how does it do that? How does a little electron get bigger than atoms when, if you just have an atom, then the electron's perfectly confined inside the atom? How do they get bigger? But they do. You measure it. So the problem is you know an awful lot about what they do, but by knowing so much, you know nothing, because it's contradictory. You have this picture of it being a little point thing in one theory. In another theory, you have a picture of it being a wave. Another picture, you have a picture of it being a cloud. Another picture, you have it emitting light, coupling to light, and having a coupling to light. So these are different views of but the same electrons. So by knowing so much, you somehow know less, because you don't know, so which will the real electron please stand up? Which of these pictures that I'm telling you about how the thing looks in different theories is the correct picture? And of course the answer has to be that they all are. But then if they all are, how?
I was going to say all of them and none of them.
None of them are the whole truth. All of them, exactly. All of them and none of them. None of these pictures are the whole truth. To get to the whole truth, you have to understand how and why it does what it does. And only then can you really say that you really understand what's going on inside these elementary particles, which are the things that then compose atoms, which then compose us, that then compose the universe around us. And when we're coming back now to the quantum bicycle, we're talking about the quantum bicycle, we're talking about just one of those elementary particles, which is seen as being a point particle, and seen as being an extended wave, and seen as being all these different things. The question then is, how does that thing that I just showed you translate into all of those things that we just talked about? How can it look like a point particle, one thing? How can it look like a wave in another? How can it get extended? How does that all work with that quantum bicycle? And that's what the quantum bicycle theory is about, and that's what Darren and Innes and myself and Martin and Viv and all these people in that washing list there are trying to find a way of describing the whole thing, everything, how all of these changes can take place. And what I was going to do was to go through a whole bunch of these and explain how all those things worked. That probably take more than the rest of today, I think, but that's nonetheless the kind of thing. Is that a good enough picture at the moment for what people thought electrons were, little point things with charge?
I think I might have seen pictures of that cloud thing.
The cloud thing too, yeah.
At first I was thinking of those molecule things you see on people's desks.
Yeah, you see there's little models with bits holding them together. Yeah. That gives a configuration of things as though they're spheres, hard spheres, which atoms aren't. They're sort of more like fuzzy blobs, but then they're sort of vibrating fuzzy blobs, which have, as I said before, this perfect oscillation, like a bell ringing, like music. Music, like harmony as well, because the oscillations are in harmony with one another. Perfect, beautiful, frictionless, eternal notes, like a note. And that's a very good analogy, actually, because the thing is vibrating, so it's like a sound. So a pretty good analogy, that. So as I say, one has different pictures of this, and one has a huge understanding. So if I'm designing a laser, then I do that using using quantum optics, which is based on quantum electrodynamics. You're looking at transitions of photons that are created, emitted and absorbed by charged particles. If I'm doing solid state physics, I'm looking at electron waves which are extended in quantum mechanical terms that are big waves. If I'm doing relativistic quantum mechanics, actually it's not very useful for anything. The actual technology we develop doesn't depend on that. It doesn't appear to be very useful. But a lot of these, Maxwell's really useful, ordinary quantum mechanics is really useful, quantum dynamics is really useful. The others here, the standard model that goes beyond these, because the standard model contains those. At the moment there are no technological applications for those things that are known about. You use the simpler theories to actually make stuff that does stuff.
Why?
Because that's what works. You use what works. So if I'm imagining, when I was imagining this single electron stuff, I'm thinking in quantum mechanics. How does that work? In order to visualize what you need to do, in order to model the thing and then have it made, because I didn't make it, but I had it made by part of my team then, our team. Then you make it and it does stuff. You're not just making something random, you're thinking what you have to do through that language which allows you to, well, to think about it. It gives you the mental tools to be able to think about what you need to do. That's how things progress. Not always. I mean, the other way to do it is copy it from somebody else and then do exactly what they do, which is quite rife, but steal it in other words. But if you want to do something new, then that's what you do. You imagine it, and then you make it, and then it does something.
So when did you first imagine this?
1991.
And how much has that shape changed?
Not at all. We got it exactly right the first time. It's a very simple shape, though. You know, it's a paradigm shape. It's a double loop. One twist, periodic boundary conditions, biting its own tail. So, but the thing is that what you get, and what Martin also did, is look, you can have that shape, but actually you don't just have that shape, you have all possible shapes. You also have this one. And as I'm moving that, I'm making, you've got to imagine just between here and here, I'm putting a thicker and thicker donut. I'm making this thing thicker and thicker. And what that does for you is it makes the outer loop get bigger and the inner one get smaller. So it's like a bunch, imagine a bunch of nested bagels, one inside another, made with flaky pastry or something, right? So you've got a thin one in the middle, which is just a ring, and then outside that they get thicker and thicker and thicker, and around each one of these is going a twist which goes round once as it goes round that donut. That's the quantum bicycle motion. So, okay. So the current understanding is contradictory, and the question is, can we find a method which will allow us to go beyond that to explain what these things really look like at a deeper level? And to do that, there's two things happening. One is the initial thing, which is this, which is literally doing what I just did, taking a model out of a piece of bendy plastic and saying, okay, what if it works like that, eh? What does that do for us? Well, it does quite a lot. You can calculate the charge, you can calculate the spin, you can calculate the properties. But what you don't have in doing that is, you know, why does it do that? No, why does it go round and round in circles? There's no why to that. There's just that. So that was back in the 80s or early 90s, in this particular, early 90s, that we first developed this particular model. What have we been doing since then? Well, we've been trying to turn that into a theory, trying to develop the maths of reality and make up theories. So what do? You make up some theories. You make up a theory. I think it works like this. And then you take that stuff, you calculate, you see whether it fits with the known stuff you have. So does it fit with everything in this book? That's a book about light, right? So is that all for? Yep, okay, that's all good. Does it fit with this one?
But if it doesn't fit with this, and this fits with that.
It can still be useful, but that's not what I'm after. What I'm after is something that fits with all of them.
Okay.
So yeah. So I'm trying to get something which is at a deeper level, and that means that it has to mesh perfectly with the things that we know that work. It doesn't have to mesh with the things we don't know that work, but when the fact that you can engineer stuff, that you can make stuff that does stuff using quantum mechanics, means there's a huge amount of truth in that theory. Do not want to throw that away, because that's an immense amount of understanding about the nature of the universe that we already have. So any theory you come up with which should really derive that, otherwise you're probably wrong, because there's all of that evidence and all of that thinking and all of that technology that you develop from the quantum mechanics. You know the quantum mechanics got to be right. The question is, how does quantum mechanics work and why does it do what it does? Not, is quantum mechanics correct? Of course it isn't. It's not the ultimate theory, because it doesn't describe everything. So it can't be fully correct because it hasn't yet got everything encompassed in it. And this is why the standard model, humans, is called a model. Look, it's not a theory. It's because actually it's a bunch of different bits that are all, including the stuff that's here and here. And this is just two of the many big books that are in this office. Well, this one, there we are. This is that's quantum mechanics. That's the third one. Well, that's a very, very short book for quantum mechanics as well. You get some big fat ones if you like. So, that's
it has a higher rate.
It does. It does. It's very hard to understand. It took me a long time to understand that book, and I studied it for quite a long time as well. So, stuff in there that I think I've got all of it now, but there are people who spend their entire lives on not understanding that stuff. And in fact, there's a truism, which is that if anybody claims they understand quantum mechanics, they're lying.
That's the point of it, right?
Pardon?
That's the point of it, is about searching.
That's right. It's a voyage of discovery, and it's certainly true that the normal formulation of quantum mechanics contains at its core something called the uncertainty principle, which is basically saying what you don't know, and how much you don't know it. And so what you'd like your new theory to do is explain what and why the uncertainty relation happens, wouldn't you? And that's partly one of the things that's slide 15 or something, right? So that's the point. You need to find something which fixes everything. Otherwise, you see, there is only one theory of how everything works. Proof. Mathematical proof, right? Imagine there are two theories that describe how everything works. Okay. You can put, each theory has a one-to-one correspondence with reality. Everything that happens in the theory happens in reality, and there is nothing that happens in the theory that doesn't happen. There's nothing, the theory doesn't predict things to happen that don't happen in reality. It's neither smaller than the whole of reality nor bigger. It doesn't say things happen that don't happen, and it doesn't not predict things that do happen. Imagine there is such a theory, but there's two of them. So you can put this one in a one-to-one correspondence with reality, and the other one is also in a one-to-one correspondence with reality. Now, if they're both in a one-to-one correspondence with reality, then they're also in a one-to-one correspondence with each other, in which case there is only one. There is only one theory of how everything works. We don't know what it is yet, for humans, but that's the job of the Quicycle Society, is to try and find it. It's the search for that theory, which encompasses all these other ones and explains absolutely everything as simply as possible. So that's the project. So
That's in the small...
No. It's not the smallest project, but that's what I'm trying to do. So
what I have to ask then is, like,
yeah,
how far off do you think we are from?
I don't know.